Alrighty, howdy folks. I think this chapter 12 section 5 is quite possibly one of the most important sections, and it's just a tad difficult. So I would like you to pay extra special attention on this one, please. Okay, equation of a line. I mean, in two dimensions, that is such a simple thing, right? Y equals mx plus b, or ax plus y equals c. One of those things just gives you the equation of a line. But in three dimensions, that's not so straightforward. So check this out. Let's say we have an xyz coordinate system. That's a 3D coordinate system. And we need to show that line. That line is actually in space. That means in three dimensions. So how do we represent how do we write the equation of this line? Well, a few things have to happen in order for us to be able to do this. One is you must have a point on the line. You must know a point on the line. So a given point. Okay. And in addition to that, you must know a vector that is parallel to this line. Cool. So as you see this vector v, that is parallel to our line. And we also, like I said, know a point on the line. Okay, those are the requirements. Now, information about that point and that vector to which it is parallel, they can be given in different ways. But eventually, that's what you need. You need the point and the vector. Cool? All right. What else? If a line L is parallel to vector v, given by its components a, b, c, and p sub 0 is x sub 0, y sub 0 is a point on the line, then the equation of L is, okay, so before I write that equation, I want to do a few things. One, can I draw a vector from the origin to that known point p sub 0? Okay, and I am calling that as r sub 0, vector r sub 0. Do you know what such a vector is called? You have a point, and from the origin to that point, we have a vector. There's a special name for such vectors. You remember? That's the position vector of that point. Okay, a position in space can be represented by this xyz coordinates, or it can be represented by this position vector. Okay, so that's one of the first things that we need to do. Let's draw a position vector to the known point. And here is pay attention to this part. This is important. When we say the equation of this line, what we are talking about is some way of figuring out every xyz coordinate on this line. That means every point on this line has a certain xyz coordinate, right? We should be able to give you, I should be able to, when I say I am giving you an equation of a line, well, I should be able to tell you how to find the xyz coordinates of every point on the line. And so what we are doing here is we are picking some arbitrary point on the line and whose coordinates are xyz. If I can tell you what xyz coordinates are for this arbitrary point, then I have pretty much told you for every point, because this point itself was chosen arbitrarily. It's not anything specific, right? Cool. And what is r? The vector r? That's a position vector to this arbitrary point P. So if I can tell you xyz or the position vector r, I have given you the equation of the line. Okay, now next, what we will do is we will draw a vector from the point p sub 0 to this p, and let's call it vector A. Now, any thoughts about whether the vector A is related to vector V? Well, the line was parallel to the vector V, right? So that means if I pick 2 points on the line like P sub 0 and P, and I have a vector going from P sub 0 to P, that vector A better be parallel to V. So who cares? We care. In other words, this vector A is nothing but a scalar multiple of V. What? Notice, if I take this vector V and multiply it by some number, let me choose a convenient number, say 0.5. What is multiplying this vector V by 0.5 do to us? Well, it gives you a vector in the same direction but has a magnitude of 1/2 of the magnitude of V, right? And if I choose to multiply vector V by say 1/4, then I have given you a vector whose length is 1/4 the magnitude of this, 1/4 the length of V, and it's in the same direction. So by simply multiplying V by different scalar values, we are able to produce different kinds of A's. Okay? And so the secret to this whole thing is to take this vector V and multiply it by a scalar to get different A's. Okay, how does that help us? R is what we want. We know R sub 0, and now we can take different multiples of V to get A. And so R sub 0 plus A gives us R. Okay, R is equal to R sub 0 plus A. A, I'm just simply saying, is T times V. What is T? T is some scalar. That means some kind of a number. So that's why we say T is an element of R. Means it's just a number, a real number. And T is in fact called a parameter. So if we take, let's see what happens. If T were to be 0, what happens? Oh, this TV would be 0. And R would be R sub 0. Would that R represent a certain point on the line? You bet. R equals R sub 0. That means this particular point on the line. Now, on the other hand, let's say if T were to be 1, then do we get a point? Yeah, that point will have a position vector of R equals R sub 0 plus V. So that means this point R sub 0, and we need to add whatever is the length of V, and so we get another point over there. So by changing T, allowing it to take on different values, we get all different points on this line. That's the strategy. And so that's what is called as the vector equation of this line L. Cool? Now, what else? Well, the position vector R, we said, is some vector x, y, z. And position vector R sub 0 is x0, y0, z0. Plus T times, let's write this vector V as ABC, because those are the x, y, z components of that vector V. So this is another way of representing exactly the same thing as this vector equation. Okay? And what else can we say? Well, is it possible to add these two vectors? x0, y0, z0 plus t times a, comma b, comma c. Can we add? Yeah. It's simple. X sub 0 plus ta, comma, y sub 0 plus tb, z sub 0 plus tc. So the x coordinate of a point on the line is x sub 0 plus ta, where t is some number. We know x0, y0, 0, we know ABC. Now all we need to do is keep changing this value of t, the parameter, and we get every point. That's the idea. And This is what is called a parametric equation. As you can see, all we are doing is setting x equal to the first component here, x sub 0 plus ta, and second component y is y sub 0 plus tb, and so on. So that's another form of this line. Okay. And finally, notice, can I subtract an x sub 0 and divide by a? Take this x equals x sub 0 plus t. Subtract x sub 0 and divide by a. Would I get a t when I do that? Well, if I were to take the second equation, second parametric equation, and say y minus y sub 0 divided by b, I would get t once again. Is this t that we got from the first equation different from this? Nope, they are the same. And so we can conveniently say x minus x sub 0 over a must be equal to y minus y sub 0 over b, and that in turn must be equal to z minus z sub 0 over c, and that's called the symmetric equation. And quite conveniently, it doesn't have that parameter t. Okay, so this is another form of the equation of a line. Okay, when we say line, it's one of those things that has infinite length, right? Stretches in both ways infinitely. However, we do know something about what's called a line segment. That's something like it just has a beginning point and an end point, unlike a ray. A ray has a beginning point but doesn't have an end point, whereas a line has no end points at all, stretches infinitely both ways. A line segment, however, is just a small piece, has a beginning and an end. So the line segment from r sub 0 to r sub 1, let us say, a position vector r sub 0 and another position vector r sub 1, and there's a line segment going from one to the other, let's say. What's the equation of that line? Check this out. This is so clever by mathematicians. They say that r, which represents this line segment, rather, let me be more precise. This r is the position vector of every point on that line segment. Pay attention to that, please. This r represents the position vector of every point on that line segment that's going from r sub 0 to r sub 1. And the way we can write this is simply say 1 minus t times r sub 0 plus t times r sub 1, and t goes from 0 to 1. Okay, what? How could this work, man? Check this out. I said this is a pretty clever thing mathematicians do, and here is the cleverness of this. What happens if we were to set t to be equal to 0? Well, look at this. 1 minus 0, r sub 0. Cool. Okay, so the 1 minus 0 is 1. 1 times r sub 0 is just r sub 0. Fine. But t times r1, oh, that's just 0. So when t is 0, what did we get? We get r equals r sub 0. Right? Well, let's say, I wish I had drawn another figure for it, but let's say this is r sub 0 and this point is r sub 1. So by setting t equal to 0, or when t takes on a value of 0, we are talking about the starting point r sub 0. All right, now let's go to the final value 1. When t equals 1, the first term goes to 0 and the second term becomes 1 times r1, or r is equal to r1. So when t takes on this value of 1, then we are at the end point. So what happens if t takes on any in-between values, 0.1, 0.2, 0.3, and 0.4? Well, we get the intermediate points, the points in between. That's the cleverness of this one. Okay, this is a way of what is called saying that it's linear interpolation. We know the end point to be, we know the starting point to be r sub 0, the end point to be r1, and we are interpolating between those 2 points in a linear fashion. And so this parametric equation is a sort of a linear representation, linear interpolation. Cool. Now let's solve some problems just to add some solidity to our understanding. Find a vector equation and parametric equations for the line. Oh, apparently we need to find what? Vector equation and parametric equation for this line. Let's recall what vector equations are. Vector equation is this r equals r sub 0 plus tv, or in fact, if you want to say x sub 0 plus ta, y sub 0 plus tb, z sub, either one of them we can say is a vector equation. And parametric equation is x equals x sub 0 plus ta, this one. Okay. Oh, let's see. So what information have we been given? Apparently the line passes through a certain point and it is parallel to a given vector. Oh, dang. This is a pretty straightforward problem. Would you agree? Because if you recall, I said in order to find the equation of a line in space, you must be given a point on the line and a vector that is parallel to the line itself. So, that point itself is p sub 0, whose coordinates are x sub 0, y sub 0, z sub 0, and the vector itself is v equals abc. Well, clearly, this is our p sub 0. Would you agree? And this is our v. Oh, piece of cake. So all the information is clearly given to us. So we are in business. We have p sub 0 x 0 y 0 is equal to 6 negative 5 2. So that means we know r sub 0 is this vector 6 negative 5 2. Would you agree? It's just taking a point and expressing it as a position vector. That's all we are doing here. And do we know v? Yep, v is abc is 1 3 negative 2/3. So vector equation is straightforward. R equals r sub 0 plus t times v. And we can write it this way. I just took the first component 6 plus t times 1 is t. So 6 plus t is the x component. Negative 5 here plus 3t, that's the y component. And 2 plus negative 2/3 t, or 2 minus 2/3 t, is the z component. Ta-da! That's the vector equation of this line. Cool. Next, recall that the parametric equation of a line is this guy. Okay, we already did everything. We have this component is x0 plus ta, and this is y0 plus tb, and this is z0 plus tc. So all we need to say is x equals 6 plus t, y equals negative 5 plus 3t, and z equals 2 minus 2/3 t, and we are done. Absolutely straightforward application of the formulas, right? Next, find the vector equation, parametric equations of the line through the point. Okay, a point has been given, and apparently it's got to be parallel to another line. You see how they change information on us? This time, good. The good thing is they gave us a point, so that means they have given us p sub 0. But they did not give us the vector that is parallel to this line, our line. Instead, they gave something about another line that is parallel to this. Like I said, we need that point on the line and the parallel vector. Is there a way to figuring out the parallel vector? We know this parametric equation, right? We know this parametric equation of the parallel line, not our line, but a line parallel to our line. We know the parametric equation. Can we make use of this to figure out the parallel vector? huh? Can we figure out the parallel vector? Okay, let's see. What is it that we have? When someone gives us parametric equations, what exactly are they giving us? When they say x equals 6 plus t, what is that 6 and what is the t? Or maybe y equals the negative 5 plus 3t. What is this negative 5 and what is this 3? Well, go to this guy. X is x sub 0, that is the x coordinate of a point on the line, plus this parameter t times a. What's with the a, b, and c? They are the components of the parallel vector. Keep that in mind. So the coefficient of t in parametric equation of a line, those coefficients a, b, and c are our vector, parallel vector. So keeping that in mind, one look at this, we can say, aha, you mean the vector parallel to this parallel line is 2, negative 3, and 9. Those are the components of the parallel vector. We are done pretty much. If we can recall all of that, we are done. So P sub 0 is clear, 0, and we can get R sub 0 from that. You agree? R sub 0 from the position vector, from the point, the coordinates of the point. We use the information about its parallel line. This is what I was talking about. The parallel line has this parametric equation, and immediately we say the parametric equation tells us that the parallel vector must be what? The coefficients of t, 2, negative 3, and 9. Cool. Okay, once we get this, straightforward. Our vector R, vector form is R sub 0 plus t times ABC. And that's it. And did they ask for a parametric equation of our line? Yeah, they did. So we just simply do this. 2t, 14 minus 3t, negative 10 plus 9t. Wait. Our line, whose parametric equation is this parallel to that line they gave? X equals negative 1 plus 2t. Are these two lines parallel? Yeah, they are. How do you know? Well, look at the coefficients of t. For the parallel line, the coefficient of t is 2, and for our line, the coefficient of t is 2. And for the y component, same thing, negative 3 and negative 3. 9, 9. Duh. So that means these two lines are both of them are parallel to that vector ABC, 2, negative 3, 9. So that means they must be parallel to each other. Check that statement out. If these two lines are parallel to a vector, then the two lines must be parallel to each other. That's the concept there. Okay, let's move on. Find the parametric and symmetric equations. Ooh, for the line through the points. Whoa. They gave us 2 points, that's all. With that piece of information, would we be able to figure out the equation of a line? If you need to, please pause the video and ask yourself, can you figure this out? What do we need? A point on the line and a vector that is parallel to our line. A point, do we know that the first part? A point on the line? Yeah, we know, in fact, 2 points on the line if you want. Which one should we use? It doesn't matter at all. You can use the first one or the second one. Okay, but what's up with the parallel vector, man? If I give you 2 points, can you find a vector from one point to the other? Yeah, that's a piece of cake, right? Head minus tail, you get that vector. Okay, is that vector going from this point to that point, is that parallel to the line? Of course it is. It falls right on top of the line, so it better be parallel to the line. You agree? If we draw a vector from the first point to the second point, that vector actually falls on top of the line, right on top of the line. So definitely we can say that vector is parallel to the line. That's all there is to it. If you grasp that concept, this problem is piece of cake. We'll take one of the 2 points as p sub 0. I seem to choose 1, 3, 4. You could have chosen 4, negative 1, 2. And we get r sub 0 from that. And also, to find a vector that is parallel to our line, we use the vector between the two given points. Okay, and v equals abc is nothing but head minus tail. 4 minus 1, comma, negative 1 minus 3, comma, 2 minus 4. That's what I did. And ta-da, that's our ABC. And once we know position vector and the vector parallel, we can do all kinds of things. This should be straightforward by now, right? What did they want? Oh, they wanted parametric, and they also wanted symmetric. Piece of cake. X minus x sub 0 over a, right? This is the parametric. I didn't even do the symmetric. Sorry about that, but it's just a simple x minus 1 divided by 3 equals y minus 3 divided by negative 4 equals z minus 4 divided by negative 2. That's your symmetric equation, folks. Cool. Sorry, I didn't get to do that. Let's see. What's that lone line segment showing up there for? Okay. Find the parametric and symmetric equations. Ooh. Whoa. Check this out. Now this is really good. Yeah, I like this problem. Find the parametric and symmetric equations for the line. And which line? The line of intersection of the planes x plus 2y plus 3z equals 1 and x minus y plus z equals 1. Well, I don't know if I... So now I'm beginning to question my smarts. Should I have put this problem here before I talk about planes? Pretty soon, right after this, I'm going to talk about planes. Okay, anyway. If you take two planes, not airplanes, just plane, like a cardboard, a piece of cardboard or a piece of stiff paper, right? That's a plane. And if you take another plane like that, and is it possible that those two planes would intersect, right? Take, I don't know, I'm not facing you, I don't have a video. This is what I'm doing right now to imagine two planes intersecting. I'm taking my right hand and opening up the fingers and squeezing them through my left hand. And so right now the fingers are sort of crossing each other. Fingers of one hand are crossing the fingers of another hand. Now can you see that as the intersection of two planes? Your right hand representing one plane, the right palm representing one plane, and the left palm facing another plane. And now watch for what's the line of intersection. Are these two things intersecting along a line? That's the idea. So this time we are being asked to find the equation of that line of intersection of these two planes. So check this out. How should I put it? Can we find a point of intersection of two lines? For example, I ask you, hey, x plus y equals 3, x minus y equals 1. Can you find a point of intersection of those two? What would you do? Well, you'll solve those two equations. X plus y equals 3, x minus y equals 1. Well, you know how to solve. You have two equations and two unknowns. X and y are the unknowns, and you got two equations and you solve for x and y. That's how you find a point of intersection. So is it possible to find the line of intersection by solving these two equations? The answer is yes. But wait. We have three unknowns, x, y, and z. But we have only two equations. What do we do about that? Well, if you have taken linear algebra, the matrix algebra, you will know that when you have two equations, two linearly independent equations, and three unknowns, you can only solve for two variables, and the third one would be just a free variable. It can take on any value, right? So once one of them takes a certain value, the other two are known. The other two have to be specific. Okay, so we'll use that concept here. So to solve these two equations, let me see, what did I say? We are given neither a point on the line nor a vector parallel to the line, right? At least not directly. At least not directly. Should I have said that? At least not directly? Okay. At least directly we are not given. Okay. To find a point on the line, we recognize the point must be on the line of intersection of the two. This means such a point must satisfy both the equations. Are there such points? Yes, there are. So this is what I'm doing. X plus 2y plus 3z, and I'm taking both the equations, and one thing I could do is try to eliminate one of the variables. That means I'm going to subtract the bottom equation from the top equation. When I do that, when I subtract x from this x, we get 0. And 2y minus negative y gives me 3y. 3z minus z gives me 2z. 1 minus 1 is 0. So we get 3y plus 2z equals 0. Okay. 3y plus 2z. That's one equation, but we have two variables y and z. Well, this is where I was talking about one of them will be a free variable. So you can make z or y to be anything you want. Cool. Once let's say we make z to be 0. What did I take? Must satisfy the above equation. Yeah, the y and z, this y comma z on the line of intersection must satisfy the above equation, this 3y plus 2z. So what I said is, suppose y is equal to 0, right? Y equals 0. Then what happens? Well, when y is 0, 3 times 0 plus, so 2z would be equal to 0, which means z would be 0. Would you agree? If we pick 0 for y, then automatically z would be 0. So y is 0 and z is 0. Well, armed with that piece of information, let's go over here to say the first equation or the second equation, doesn't matter. And maybe simple, this one would be much simpler. X minus y plus z. Well, plug 0 for y and 0 for z, and you get x equals 1. Right? So we know one point on the line of intersection must be 1, 0, 0. Cool. Look at how we are doing this. All right. What about another point? Earlier, in this case, we took y to be 0 and figured out z based on that. What if we were to take y to be... did I not copy? I think I picked different values. Okay, anyway. I think... Come on, man. Let me pause here and download another one, please. I'm sorry. Okay, I'm back. I don't know. So if you see me hesitate like this and pause, and at least in this case, it's just so happened that I create all these PowerPoints on my desktop, and then I copy them onto this laptop. Somehow the video card, or graphics card or audio card, something is not working on my desktop, so I have to transfer it onto this laptop and all this. And okay, anyway, I don't want to bore you with those details. Looks like I thought I changed these numbers, but anyway, we could go with these. I just happened to pick z equals 3, I think, folks. If I pick z equals 3 and solve for y, check this out. Why did I pick z equals 3? Because this would be 3y equals negative 2z, and negative, so y itself would be negative 2z over 3, right? I wanted to get rid of that 3 in the denominator, so I made z to be 3. I could have made z to be 6, a multiple of 3. As long as I do that, I'll be fine, okay? So I pick z equals 3, and y is negative 2. Now, armed with these two values of y and z, let's go to one of these equations and figure out what x ought to be. So it looks like it's much simpler to use the second equation. And so we have x minus negative 2 plus 3. So that would be x plus 5 equals 1. So x equals negative 4. Solve for that. And so that means negative 4, negative 2, 3 must be another point. Right? Cool. So what happened? We are in a situation where we seem to know 2 points. And so we are pretty much done. Just like the previous problem. Once you know 2 points, you are in business. Find a vector by doing a head minus tail of those 2 points. And that's the parallel vector. And we already know one of these points. You can pick 1, 0, 0 or this one. And ta-da, we got the equation. Okay? All right. This is the parametric equation. I didn't do the symmetric in this either. Would be simply x minus 1 divided by negative 5 y over negative 2 equals z over 3. That's what the symmetric equation would be. Ah, I did do that. What do you know? Okay, and so we got both the parametric and symmetric. And in fact, we got the vector equation too. All right, let's see. Find the vector and parametric equation for the line segment. You remember that line segment thing? 1 minus t times r sub 0 plus r sub t r sub 1. That's it. As simple as that. And of course, you better mention that 0 less than or equal to t less than or equal to 1. Okay. And so just simple plug and chug, and we're done, folks. That's a ridiculously simple one, but you need to know. Cool. All right. What's up with this? Oh, okay. And next problem is determine whether the lines L1 and L2 are parallel, skew, or intersecting. Ah, this is a good one. This is very interesting. What are we given? We are given two lines, equations of two lines. In what form? What's that? What form is that? X over 1 equals y minus 1 over negative 1 z minus. That's a symmetric equation, right? And similarly, L2 is given in the form as in the form of a symmetric equation. Okay, and now they're asking, hey, are these two lines parallel? Or do they intersect? Or are they skew? What in the world is skew? Do two lines have to be either parallel or intersecting? In two dimensions, that's got to be the case. You draw two lines, one of two things will happen. Either they will be parallel or they will intersect somewhere. But 3D, that is not necessarily true. What? How come, man? Okay, wherever you're sitting, do you have four walls? Okay, look at the line that is to your right from top to bottom in one of the corners. Right, you have one wall intersecting another perpendicular wall, and there's a vertical line, right? That line of intersection. That line, keep that make that to be one of your lines, and pick to the left wall the line on the ground. Okay, left wall going from back to front, a line along the maybe I should have bottom when I say the floor and the wall to your left, right? There's a line of intersection which is horizontal. Now that line and this vertical line, that horizontal line to your left and this vertical line to your right, are they intersecting? No. Are they parallel to each other? No. Right? They are neither parallel nor intersecting. So that can happen. And when that happens, we say the two lines are skew. And so we are being asked to find that. Fascinating. Okay, so what do we do? Well, do these symmetric equations allow us to figure out a vector that is parallel to each of these lines? Can we figure out a vector that is parallel to L1? Can we figure out another vector which is parallel to this L2? Can we use the information about those two vectors to figure out whether these are parallel or intersecting or something like that? The answer is yes. And I seem to be saying the vector that is parallel to L1 is V1, and that is 1, negative 1, and 3. Where did I get that from? Well, recall, the symmetric equation is what? X minus x sub 0 over A, y minus y sub 0 over B, right? Equals z minus z sub 0 over c. So the denominators are in fact a, b, c, which are the components of the parallel vector. That's all I'm doing here. So 1, negative 1, 3, that's what v sub 1 is. Now look at the denominators of this, and you get 2, negative 2, 7. That should be the parallel vector for the second line. Okay. Are these two vectors parallel? If they are, what should happen? Their cross product must be 0. The cross product of two parallel vectors is going to be 0, right? So let's figure out the cross product. And so v1 cross v2, I just did this, and I get negative y minus 3j, and that's not equal to 0. So all we can say is, nope, the vectors are certainly not parallel. We cannot say whether they are intersecting or skew, but we can certainly conclude they are not parallel. Okay, so how do we determine the point of intersection or whether they are skew? To find skewness or intersection, we need to write the two lines in parametric form. Oh, interesting. So we take the symmetric equations and convert them to parametric form. But there's one caveat though. Do not use the same parameter for both of them. Parameter happened to be t, right, up until now. Don't say t for both of them. Just use a different one for the other one. So if we were to do that, use parameter t for the L1, then this simply becomes x equals t and y minus 1 equals negative t, y minus 1 over negative 1. Each of these is equal to t, right? So if you know that, then from that you can figure out this parametric equation. Z minus 2 equals 3t or z equals 2 plus 3t. And for L2, let's use a parameter s. So we get x equals 2 plus 2s, y equals 3 minus 2s, and so on. Cool? Okay, now what? Notice, if the two lines, pay attention to this please, if the two lines intersect at a certain point, then the x, y, and z values of one line must be exactly the same as the x, y, and z values of the other line at that point. Would you agree? Let me repeat that. When two lines intersect at a point, at that point of intersection, the x, y, z coordinates of one line must be exactly the same as the x, y, z coordinates of the other line. That's why that's called a point of intersection. It is common to this line as well as that line, right? Okay, keeping that in mind, now we can say, wait, you mean the x coordinate here must be the same as that x coordinate? That gives us a relationship between t and s. Check this out. By recognizing, say, any one of them, this x coordinate on the first line is the same as the x coordinate of the second line, we get a relationship between t and s. Okay. T is equal to 2 plus 2s from x. Would you agree? T must be 2 plus 2s. Okay, now what? Use that value of t equals 2 plus 2s and figure out what y should be. Go to the first line. First line is in terms of t, 1 minus t. But instead of t, use this 2 plus 2s. Okay, 1 minus, is that what I did? Well, I seem to have figured out z. Okay, let's calculate z based on this t. So 2 plus 3t, but t should be replaced by 2 plus 2s. And when you do that, you get 8 plus 6s. So the z coordinate of L1 is 8 plus 6s. Is that what the z coordinate of the second line is? No, it is 7s. Is 8 plus 6s equal to 7s? Nope, it's not. Guess what? The lines must be skew. This point, so they do not intersect. Or maybe I should put it that way. The fact that when we took this t and figured out what z ought to be from the first line by substituting for t in terms of s, what we get for z from the first line is not the same as the z for the second line. And notice they are both in terms of s only. Is 2 plus 3t equal to 7s? I don't know. Because one is in terms of t and then the other one is in terms of s. But if we express 2 plus 3t in terms of s, now we are comparing apples and apples. We can actually talk about whether or not 8 plus 6s is identically equal to 7s. And the truth is, nope, it's not equal to. So that means these two lines do not intersect. That means, and we already established that they are not parallel, so they must be skew. Right? Very important problem. I am very likely to ask you a question like this. So please be sure to learn this. Okay? What else? Ooh, equation of a plane. Maybe I'll pause this video. It's pretty long and I'll record this as a second video. Okay? Cool.